This will be your last lecture on the chapter order relations, and in this video I'll be discussing some important notions that we have in order relations and the examples which we require to be discussed while discussing this notion. Now, most of the concept are taken from the past chapter, that is relations, and this is a special category of that relations we will discuss in this chapter. So most of the examples I would try to avoid justifying, and I'll just state it as you can do it by yourself. Okay, and if you want to discuss some more properties on this particular concept of on this particular chapter, then you may refer the textbook Foundation of Mathematics by Kumaresan, Ajit Kumar and Bhaba Kumar. So let's begin with this partial order relations and the total order relations. In the chapter relation, we have come across a different kind of relation. We have seen the definition of relation, a relation on a set and relation between two sets. We have seen that relation on a set X is nothing but the some subset of X cross X, and relation between two sets X and Y is nothing but the subset of the Cartesian product X cross Y. And there's a special class of relation which we called as an equivalence relation, which is defined on a set itself. So relation defined on a set itself is said to be a relation defined on a set X is said to be equivalence if it is reflexive, symmetric, and transitive. Right? Now, if you remember in the analysis, we have discussed one order relation that's called as less than equal to relation. Okay, and this is called as an order relation because it satisfies all the properties of so called as an partial order relations. Okay, so we will discuss now in the same way, just like an equivalence relation, we will discuss the partial order relation and the property of set with the partial order relation. So we say that a relation R on the set X is a partial order if it is reflexive, antisymmetric, and transitive. Reflexive means for each point in X, X is related to itself X. Antisymmetric means for any point X comma Y in X, whenever X is related to Y and Y is related to X, this implies that X is equal to Y. And the transitive means whenever X is related to Y and Y is related to Z for any X, Y, Z in X, this should imply that X is related to Z. Now, most often it is denoted with this notation. Now, this is not the standard, this may not be always the standard less than or equal to notation. Okay, although that's a notation that we use to denote a partial order relation, just like to denote the equivalence relation we use tilde. So we use this relation, or to avoid the confusion you may make it in this way, because most often students stick to this notation and they read it only as the standard less than or equal to relation that we have in a real analysis. Okay, so we write this as, instead of R we write it as, when X is related to Y, X R Y. This is the old notation. If it's a partial order, then we write it as X is less than or equal to Y, and we read it as X is less than or equal to Y. Okay, so basically X is related to Y. Now the set with this partial order relation is called as a partially ordered set, or it is also called as a poset. Okay, now if X is less than or equal to Y holds, that is, if X is related to Y through that partial order relation, and if X is not equal to Y, then we write it as X is less than Y, or we say it as X less than Y, and we write it in fact in this way: X is less than Y. Okay, So now, if I go further, that how do we write x is not related to y through via the partial order relation? So that's it. This is a notation. We just strike out that less than or equal to, and we read it as x not less than or equal to y. This would not implies that y has to be less than x, less than or equal to x. That is true only when a set is a totally ordered set. So that we will see in this definition, the what you mean by a total order. Most often we discuss a set which is totally ordered. Okay, so a partial order, so again a relation which is partial order is called as a total order if for each x comma y in x, either x is related to y or y is related to x, to that relation. Again, I read this as the related most often, or I just say it as a less than. So you need to understand that it is not a standard less than or equal to relation. Okay, it is some partial order relation that is defined on that particular set. So in this case, the set x with this relation is called a totally ordered. Sometimes we simply write it as x is a totally ordered, which when you need to understand that the order relation that is defined on is a totally ordered, it's total order. Okay, so now we are ready. Now this is something, something analogous to law of trichotomy, which we have with the standard order relation. So if x is totally ordered, we know that you take any 2 points, they will be related by some way. That is, either x will be related to y or y will be related to x. So both is possible. So if x is not related to y, and if x is totally ordered, then definitely y has to be related to x. Otherwise, the given set won't be a totally ordered. That will contradicts to the definition of totally ordered. So if x is not less than y, this should implies, that is, x is not less than y as well as x is not equal to y, which means that only option, only possibility for y and x is left in the totally ordered set is y is less than x, which means that y is related to x but y is not equal to x. Okay, so let's get into some examples, some standard examples. As I said, the first example would be example of r along with the standard relation that is less than or equal to. First one, uh, r with this is a poset, right? It is a poset. Is a poset because this is the standard notation, less than or equal to. It's a reflexive because for every x in R, x is less than or equal to x. It's a antisymmetric, that is whenever x is less than y and y is less than or equal to x, this implies that x is equal to y. Q2, that is whenever x is less than y and y is less than z, this definitely implies that x is less than z. The question is it now? So we have, it's very easy to show that this standard relation less than or equal to is a partially order, and so that r with this relation is a poset. This is the standard less than. Is this a total order? Is total order on? In that case, we can say that r itself with the relation is totally ordered. And yes, this is true. This is analogous to a law of trichotomy. If we choose any two element, we can relate them. If I have any two element in R, by law of trichotomy, either x is less than y or y is less than x or x is equal to y. Exactly one of the following is true. Okay, exactly one is true, and this is by law of trichotomy. And because of that, the set R with this relation is totally ordered. That is, sorry, this is on R. That is, the relation is total order. Beside this, let's define another relation. You know, for any set x we will contain the relation defined on the power set of x. The standard relation that is defined on this power set of x is contained in. We say that A is related to B if and only if this A and B are the subset of x, as is the relation is defined on the power set of x. A is related to B if and only if A is contained in B. Okay, so that is the relation. So for any set, we have this as the relation. Now the question that is defined, I mean, is this the partially ordered set? Is this a poset? Okay, and it is trivially true. One can very easily check that this relation is reflexive because every set is contained in itself. Then it is antisymmetric, that is whenever we have two sets with the two subset of x with the property that A is contained in B and B is contained in A, then this should implies that A is equal to B by the definition of equality of two sets. And thirdly, whenever we have A is contained in B and B is contained in C, then obviously A will be contained in C. Then so therefore this is partially ordered set. Okay, now the question is this a totally ordered set? Is this a totally ordered set? Okay, so this is not this in general is not true. Just think of it. Okay, the totally ordered set means given two subsets of x, will it always be relatable? That means will it always be true that A is a subset of B and B is a subset of A? This is definitely true if x is a singleton set. If x is a singleton set, then there are only two possible subset of x, that is an empty set and that singleton set itself. So in that case, we can have only two choice of a subsets, that is empty sets and the set x itself, or empty sets and empty set and the set and set itself. Now obviously these are relatable, but if x contain more than two elements, let me take x containing a comma b for some a and b. Okay, a is not equal to b, right? So in this case, if I choose a set singleton A, this is a subset of x, and if I choose a set singleton B, which is a subset of x, then A is not related to B because A is not a subset of B, as well as B is not a subset of A. So we could find two sets in the power set of x which are not relatable either way, and therefore if x is a set containing more than one element, then it is not to a total not a totally ordered set. Then this is not a totally ordered set. So therefore if x has more than one element, then p of x with this relation is not totally ordered. So this is another example which is wherein the relation is defined on p of x. Okay, the next relation we can consider on n. We define it as m is related to n if and only if n is a multiple. I mean, in this case you can say that m divides n, or n is a multiple of m. Remember that it is defined on a set of a natural number, so we use n is a multiple of m. So this relation, if n is a multiple of itself, we know that it is reflexive. Then if a is a multiple of b and b is a multiple of a, that is a divides b and b divides a, we know that a is equal to plus or minus b. But this is the relation defined on n. So in that case, in fact, we have seen that it is antisymmetric too, and this is what is it, this is transitive also. So therefore this is partially ordered, and so set n with this relation is poset. But then the question is this, so here the set is strictly mentioned as n, so precisely mentioned as n, so you know the set very well. So this is not the relation in general on any set. So the question is now, is this relation is totally ordered? So you need to ask a question for yourself. So can you find 2 point in a set of natural number wherein they are not related either way? That is, suppose I have 2 points m and n. M is not a multiple of n as well as n is not a multiple of s. Easy choice. You select, you consider any, say, prime number, say 3 and 5 in n. 3 is not a multiple of m, 5, and 5 is not a multiple of 3 is not a multiple of 5, and 5 is not multiple of, and so therefore 3 is not related to 5 and 5 is not related to 3. So we could find a pair in n cross n such that that pair is not related either way, and therefore I can say that n with this relation is not totally ordered. Okay, so these are some examples of partially ordered and the total order. Now for more example, you can refer the textbook and you may try to solve by yourself. Now even the relation defined on cross product, I will take one more example. So suppose I have this and these two sets. Okay, now there are natural way of defining the relation on x cross y. That is one relation, that is, you say that x1 comma y1 is related to x2 comma y2 if and only if x1 is related to x2 through the relation x and y1 is related to y2 through the relation on y. Okay, so this is one relation, the natural way of. The other one is called as the lexicographic or the dictionary order on x cross y. So suppose these are some partially ordered set with the same, with some partial order relation. We don't know what exactly, but as per the notation, it may be the same relation. So B partially ordered set. So on x cross y, if you remember, we define a relation in this way: x1 comma y1 is related to, I'll use beta different notation for the relation, as this relation is already used. X1 comma x2, x1 comma y1 is related to x2 comma y2 if and only if either x1 is related to x2 and it is not same, or x1 is equal to x2 and y1 is less than or equal to y2. That is, y1 is related to y2 or y1 is same as y2. If x and y individually are totally the partially ordered, then we claim that this relation x cross y along with this relation is totally ordered. Okay, so one can prove this, no justification I'll not mention. And further, if x and y are also totally ordered, then x cross y along with this relation is also totally ordered. Let's talk about some more terminologies that are defined in this particular chapter. So we have first we will talk about the restriction of relation. The way we have a restriction of a function, we do have a restriction on relation. So let R be a relation on x and y is a subset of x. The relation r power dash on y defined by, see, y is a subset of x, so the same relation we can define on y. So the same relation which is considered as the new relation as the set is changed. So this relation is called as the restriction of R on Y. So y1 is related to y2 through R prime in Y if and only if y is related to y2 through R in X, and this is called as the restriction of R on Y. Next definition is a chain. A non-empty set Y of a partially ordered set X with the standard order with the order relation, with the partial order relation less than or equal to, is called chain if that subset itself with the relation less than or equal to is a totally ordered set. Okay, so a quick example over here. Suppose I have a set with the divisibility relation. So the set X is defined, we have taken some subset of natural numbers, say 1, 2, 3, comma 4, comma 5, comma 6, comma 9, comma 12, comma 18, comma 24. With the partial order relation defined by, say X is related to Y if and only if X divides Y. Okay, so the divisibility relation, it's a partial relation. Now if I consider the set A along with I mean as a subset of X, by the way this is order relation. Okay, so if I consider say 1 comma 2 comma 4 comma 12 comma 24. Okay, and if I consider this, first of all you need to check whether this is totally ordered as the with the same relation defined on X. Okay, so we are actually looking for the relation restricted on this set, is it a totally ordered or not. If it is not, then we cannot say that this is a chain. If this is totally ordered, then definitely this is chain. Now we know that 1 is related to 2, 1 is also related to 4, 1 is related to 12, 1 is related to 24, because 1 divides every other number, right, every other natural number. Now if I collect any two, the question is, if I collect any two member from this E, are they going to have a relation? Will they, I mean, suppose I choose X comma Y from A, will X will be related to Y or Y will be related to X? That is, will X divides Y or Y divides X will hold. Okay, so that is trivially true. You can just look at this statement, this set. But if I choose A as the whole set X itself, that will not be true, because it is not the total order relation on this set X. Because if I choose 2 and 3, neither 2 divides 3 nor 3 divides 2, and therefore that any set containing 2, 3 or any such set wherein two elements or the pair in that particular set is not relatable, is cannot be set as a chain. So in this case A is a chain in X as A with this relation is uh, A with this relation is totally ordered. Okay, so in fact we need not say that A with the relation, I can simply say that A is a chain on X in X. If I choose say A1 as 1 comma 2 comma 3 comma 5 comma 6 comma 9 comma 12, this is not a chain. Clear reason? Because if I restrict the relation on this, then it is not a total order relation. Okay. Yes. So next term that is defined over there is the lower bound and upper bound. Now this lower bound and upper bound is defined in terms of order relation. Now, in the analysis, when we have discussed this in the real number chapter, then that time we have considered the order relation as the standard less than or equal to relation. Okay, so now how do we replicate the same definition for this? First of all, we can define this terminologies only on that set with the partial order, only that set which is partial ordered with respect to some relation. So suppose I have x with less than or equal to is a partial ordered set, and if A is a subset of x which is non-empty, then I can define upper bound and lower bound for that particular set. Now we can say that the given set may not have upper bound and it may not have a lower bound. So what is an upper bound? An element u in x, it need not be an element of A, is called an upper bound of A if for all A in A is related to u through the relation less than or equal to. Now again, let me remind you that this is not the standard less than or equal to relation. It may be, as you can see, that it may be a division as well as, or it may be the relation defined on the power set of x with the standard relation over that is a subset. Okay, so we simply say that A is related to u through this relation less than or equal to. A is less than or equal to u, which means that A is related to u. So this is true for every A. So every element of A is related to U. In that case, we say that U is an upper bound. Similarly, an element L in X is called lower bound of A if for A in A we have L is less than or equal to A. That is, L is related to every other element of A. Every element of A, then we say that L is a lower bound. One thing to be pointed out, that this U and this L, upper bound and lower bound respectively, may not be coming from the set A. Okay, so if that is true, if that upper bound and lower bound is an element of A itself, then it is called as the maximum of A and minimum of A respectively. Okay, so let me take one example of upper bound and lower bound. Just look at this. Consider R with the standard relation, standard less than or equal to, with the standard order. Okay, so first set, I'll take A to be close interval 0 and open from 1. Now you can see that 0, by the definition of this set, all the element x belongs to A means what? X will be lying in between 0 and 1. 1 is the upper bound and 0 is the lower bound. Okay, you can see that 1 is not a part of this 0 comma 1, and in fact no upper bound lies in this set A, and therefore it do not have a maximum element, and 1 is not a maximum in this case. Whereas if you look at this lower bound, 0 itself is a lower bound because every element of x is such that 0 is less than or equal to that. Every element of A is such that 0 is less than or equal to that element, and therefore 0 is a lower bound and 0 is the minimum too because it belongs to the set A itself. Now if I for the same one, if I consider B to be the set of all x in R such that x is greater than -1, this is basically the set -1 comma infinity. Now this set do have the lower bound -1, it do not have an upper bound. Okay, no upper bound because there is no bound from the right side. Okay, and the lower bound here is -1. You can also consider -2, -3, -3.5. All these are lower bound, but none of the lower bound belongs to this set, and therefore it do not have the minimum element. In fact, one exercise for you over here is that if the given partial ordered set has a maximum and a minimum, if the given subset of a partial ordered set has a maximum and minimum element, true that it is unique. So now let's talk about, since we have seen that given a upper bound it is not unique and given a lower bound it is not unique, how do we get the unique upper bound and lower bound? So we from the upper bound we choose the least among that, because that is unique. As you know that if you have one upper bound, then any other upper bound which is greater than that upper bound is also upper bound. So therefore we choose the least upper bound. So what's the definition of least upper bound? We call alpha from an x. It need not be an element of a. Alpha in x is said to be a least upper bound if, or it's also called as a supremum, if alpha is an upper bound of a, and for any upper bound beta of a, we have alpha less than or equal to beta. That is, every other upper bound will be greater than or equal to this least upper bound. And similar statement you can make for the lower bound also, that is the greatest lower bound, which is also called as the infimum. So that I will leave for you. So called as a maximal and the minimal element. So if we have a partial ordered set, we say that an element x naught is a maximal element if whenever a is in x and whenever x naught is related to a, that is x naught is less than or equal to a, this should imply that a is equal to x naught. What mean, what this mean is that it's a maximal element if it is not related to any other element of x other than itself. We know that x is related to itself to the partial order relation as x naught is related to x naught to the partial order relation as it is reflexive, but it is not related to any other element of x. So whenever that is true, this means that that element is equal to x naught. And same way minimal is what we say, that y naught is a minimal element if b belongs to x and y naught is greater than or equal to b, that is b is related to y naught, implies that y naught is equal to b. See, from the picture it should be clear, maximal element will always be placed on the top and the minimal element will always be placed below. What this mean is that minimal element may be related to some element, but no element from x will be related to, no element from x should be related to this element, then only we can call it as the minimal element, other than, of course, other than the element itself. Okay. And the maximal is that, if we just represent the arrow by this thing as a relation. See, I say that this is related to this element is related to this, then there shouldn't be any arrow going from this elements to any other element of that x other than itself. See, reflexive we do not denote by an error, it will form a loop. Okay. So that's how the maximal and minimal elements are defined on a partial ordered set. Now I would take an example through which you will easily understand what basically we are talking about as a maximal and a minimal element. Let me consider the set X with the power set of, say, some set S, okay, with the inclusion relation. Now in this set, see, here in the power set of S, it contains all the elements starting from empty to S. Can you tell me which is that set which is not contained in any other set? Which is that subset of X which is not contained in any other subset of subset of X, and it is contained only in that set? Obviously, the set S itself. S is not contained in any other than S, any other set other than S. Okay, so definitely this is becomes a maximal element Okay, and the minimal element will be empty set, because no other subset of S is contained in the empty set other than empty set itself. Okay, so that is placed, below. And this is so called as an hash diagram. If you go through it, you will clearly understand that the minimal element are placed below and the maximal element are placed on the top. So these are the only two elements that we have as a maximal and minimal element respectively. Now I'll slightly modify this. Instead of considering simply p of s, I'll remove an empty set and the set S itself from this P of S with the same relation, that is inclusion. Okay. Now in this case, can you guess what should be the maximal element? Definitely X S. If it was in the power set of S, if it was in the set X, then it would have been a maximal. Now we have removed S. Okay, so what could be at the maximum position, or which set could be that set which is related to itself and which will not relate to any other element of S. So can you think? It will definitely a set with one element short of S. Okay, that is, it's a set containing all the element of S except one. If it contains all the element, then it will definitely be S, but S is not a set X. If it contains two elements short, then it will be related to a set with all the element except that one element, one among those two elements. Okay, so that will be true. So in this case, a set which has one element less than this S is going to be the maximal. And definitely empty set cannot be a minimal, as it is not in the set X itself. So can you think what could be the maximal? All the singleton set S. Okay, so if, for our convenience, let us say that S is finite. Otherwise there will be a problem. There will be a countably many maximal, and there will be a countably many minimal. Okay, but we can actually produce a proof for that even if S is infinite. Okay, so we will consider the set of the form S difference T. You will have to remove each T from S, so that will give rise to each minimal. So for example, S is just a singleton set A comma B, so A comma B comma C. Then all the sets of the form A comma B, then B comma C, then A comma C will form the maximum. S itself is not in the P of S, so these are the only maximal that we'll have. So in this case, see, just look at the first element A comma B, it do not contain C, B comma C, it do not contain A, and A comma C, it do not contain A. Now here I cannot say that this is the maximal element, because this is related to A comma B. This is contained in A comma B, as well as this is contained in A comma C. Okay, so these are the only possible choice for the maximum. So what I'll do, I'll define S to be define A to be S difference singleton T for T in S. Okay, now I'll for our convenience, let me take it as A suffix T, so that we will get to know that we have a different AT source here. So we will prove that these are maximal for each T in S. Okay, now how do we show that it is maximal? Let B be an element in X, that is B is some subset of S not equal to S not equal to empty set, such that we will take see the definition of maximal element. Where is it? Yes, such that X naught is related to A, the maximal element is related to A, then we should prove that A is equal to X. So I'll take B is related to, or yeah, A is related to B, such that such that A is related. I want to show that this AT is maximal, such that AT is related to B for some T in S. So our claim is that this AT is equal to B. Okay, right? So that is true. Now if AT is not equal to B, then what will happen is that AT will become a proper subset. It's already a subset of B. If it is not equal, then in that case it is a proper subset. So then B has at least one element of S which is not in this AT, right? So then B has at least one element of S which is not in A, right? Fine. So but the only element of S which is not in A is T, right? But the only element of S which is not in A is T. AT, by the way, AT is T by our definition. Hence A union AT union this T should be contained in B, right? Because see, now we know that AT is a short of only one element from S, that is T, and we are saying that AT is a proper subset of B. B says that AT is a proper subset of B. So that means what? There is at least one element of S which is not in AT. But the only element of S which is not in AT is T, right? And therefore, if I take the union of AT with this T, it has to be contained in B, which means that the entire set S is contained in B, right? And therefore this would implies that B is equal to S, which is contradiction, because B is coming from X, and that means B is different from S and B is different from empty set. So that is the contradiction that we are getting, because we claim that AT is not equal to B. Okay, so therefore the only possibility for AT is that it is equal to B. This is true in fact for each T, and therefore one can say that AT for each T in S is maximal. I won't say that it is the maximal, okay, because it need not be unique, as you can see in this example, maximal of X, okay. And in a similar way, one can prove that all the singleton set, similarly you can prove that all the singleton set T for each T belongs to S is minimal of X. You need to do little work over here to prove that it is minimal. So with this I end up the session on this chapter, and as I said, this was the last lecture on partial order relation and on this chapter. Now there are some more exercises and the problems given on the textbook. You may refer to the textbook. So thank you for watching this video and have a nice day ahead.